Finally, in this last lecture, we'll take a look at some newer technologies, in particular strain imaging and elastography. I'll begin by talking about a technique that's fundamental to these that's called speckle tracking. The idea is, as the name suggests, it's possible to track the speckle pattern in tissue from one image to the next. So here I'm showing a small region of interest which the machine has defined. The machine then analyzes the speckle pattern from that small region of interest and looks at the way it changes from one image to the next. So I've highlighted in this particular example a black circular area, and you can see that from one image to the next it is moving downwards and to the left. The machine can automatically track this motion, so it can calculate the speed and direction of movement of that tissue, and therefore it is doing something similar to Doppler. The big difference, though, is that this is a two-dimensional measurement of motion. So we're no longer looking at just the movement parallel to the beam, as we are with Doppler. We're now looking at the movement in two dimensions, so we get both the speed and direction of motion from the ultrasound information. So this then enables a couple of different applications, which I'm going to go on now to describe. First, though, I want to look at the measurement of tissue elasticity, because this is fundamental to the subject of elastography. Imagine a cube of tissue or a volume of tissue, and it has a linear dimension which I've indicated as x1. Suppose I then apply a force to it, and that causes a compression of the tissues, as I'm showing here in the second diagram. So now that linear dimension has been squeezed down to a smaller amount, x2. So the application of the force has compressed the tissue. We use the word stress to describe the force per unit area. Now this, of course, is simply what we mean by pressure, force per unit area. So the stress really has the same dimensions as pressure, and indeed stress is measured in pascals, in the standard units that are used to measure pressure. So that's stress. It's the applied force per unit area. Then we want to characterize the compression of the tissue. So what we do is we look at the relative change of that x dimension. So in other words, the change of the x dimension divided by its initial value. So that's going to give us the relative change. Now, as well as linear strain, there are other kinds of strain, and there's volume strain, for example, or shear strain. But in this case, we're just looking at the simplest, which is linear strain. So then we have a number which is used to characterize the elasticity of any material, and in our case, of tissue. And this is known as Young's modulus, and that is simply the ratio of the applied stress divided by the resulting strain. Now, strain is a change of dimensions divided by a dimension, so it actually has no units. And so Young's modulus also has units of pascals, because it's a measure of the stress divided by the strain. So Young's modulus characterizes the elasticity of tissues. If a tissue is very stiff, then there will be little compression, and so the strain will be small, and therefore the Young's modulus will be large. The ultrasound machine can measure strain. It does this by defining two or more regions of interest. It then uses the speckle tracking technique that I've described to look at the movement of the tissue in each of the regions of interest. If the tissue is being compressed, for example, there'll be a difference in the motion in the different regions of interest. The machine will be able to look at the motion in each region of interest, work out the differential motion, and therefore calculate the strain. Here we have an example of strain imaging in the heart. So the machine has identified the myocardium, calculated the strain at many points around the myocardium, the linear strain. It's then broken the myocardium up into segments and plotted the strain and the way it varies through a single cardiac cycle. Strain imaging, in this case, is looking at the natural change in the dimensions of the myocardium that result from its normal physiological function. Elastography is going to do something a little different. It's going to look at the strain in tissue caused by an externally applied force. So here we have the normal kind of elastography, standard elastography. You'll see that we have a grayscale image, and then we have, as in the previous diagram, a color overlay. But in this case, the overlay is indicating in a qualitative way stiffness of the tissues. If you look at the color bar, you'll see that very soft tissues are shown in red and very hard tissues in blue. And there's a gradation of colors in between. So the color overlay just shows in relative terms which tissues are more or less stiff. So how is this done? Well, again, the machine is going to be using speckle tracking to look at the tissue motion. And as I said, there needs to be some sort of force applied to the tissues to cause compression and expansion. That may simply be physiological forces, for example, due to respiration or due to transmitted arterial pulsations. Or it may be induced by you, the user, for example, by pushing on the probe. So you may simply push the probe in and out on the patient's skin surface and look at the motion of the tissues in response. As I said, the machine calculates the strain using speckle tracking and then gives a qualitative indication of the relative stiffness of the different tissues. There's another technique entirely that's also used to do elastography. I should explain, by the way, that the concept for elastography came about from the observation that manual palpation is a very, very useful clinical tool. Clinicians can acquire lots of useful information simply by palpating tissues, looking for abnormal stiffness. So the idea with ultrasound elastography is to extend this to deeper tissues that aren't readily available for manual palpation. So coming back to this technique that I'm describing here, shear wave elastography involves the generation of a shear wave in the tissues. A shear wave is rather like a shock wave. It'll travel through the tissues, and the machines are built to have extremely high imaging speeds that allow the machine to actually track the movement of the shear wave as it travels through the tissues. So the machine is able to calculate for each point the propagation speed of that shock wave at that particular point. This is useful because the propagation speed at any given point is mathematically related to the elasticity of the tissues at that point. So having measured the propagation speed at each point, the machine can calculate the elasticity in quantitative terms. So you'll notice here that we have a color overlay again, and we have a color bar, but the color bar now is calibrated numerically in kilopascals. So it is showing us values of the Young's modulus at each point. The high Young's modulus, remember, corresponds to stiff tissues, and that's the reddish colors. An example of applications of this technology is in tracking liver disease. So fibrous degeneration of the liver, fatty degeneration of the liver, cirrhosis, and so on. So shear wave elastography has become a very valuable quantitative tool, providing quite different tissue properties than standard ultrasound imaging. Now, I mentioned this requires extremely high imaging speeds. How does the machine achieve that? The answer is that the machine uses plane wave imaging, or more generally the term is synthetic aperture imaging, to create an entire image with a single pulse. So just imagine that you have a probe and every single element in that probe transmits at the same instant. This will generate a flat wavefront which simply travels into the tissues, interacting, scattering and reflecting. On the right I'm showing one particular scatterer sending echoes back. The machine is going to receive the echoes on every single transducer element. Those echoes are going to arrive at different times, and by looking at the arrival times of the echo, the machine can calculate the exact location of that scatterer. So in practice what happens is the machine receives the echoes from every single element, digitizes that information, and then of course it will end up with a mass of digitized echo data for every single element. That data it then goes into a computation which produces an ultrasound image. So you can see this is rather similar in a way to CT imaging, where you collect a mass of data and then the machine computes an image from that data. There are two clear advantages to this way of making images. The first, of course, is that you're making an image with a single transmit pulse, and so you can have extremely high frame rates of 1,000 images per second or more. The other advantage is that the image will be focused optimally at every depth. So there's no longer any need for the user to select a particular depth to focus at. The image will be automatically focused at every depth. Now there are disadvantages and very major engineering challenges in doing this. So at the moment, the machines which use this technique are actually using a sort of hybrid, somewhere between this technique and conventional imaging with the formation of beams, stepping of the beams, etc. So at the moment we're sort of in a transition time between the conventional technology which I've described in my earlier lectures and this new synthetic aperture approach. It may well be that the future of ultrasound will become synthetic aperture imaging purely, but there are now machines producing extremely high imaging rates using an adaptation of this technique. Here's another application of the high-speed imaging. With very high-speed imaging, it becomes possible to do speckle tracking on moving blood. And so this diagram shows you the results of doing speckle tracking on the carotid bifurcation and the adjacent jugular vein. The arrows show you the speed and direction of motion of the blood at different points. This is referred to as vector flow imaging, vector velocity imaging. And you can see, of course, on the top left, if we look at the color bar, that we have got absolute velocities because this is not a Doppler-based technique. This is using speckle tracking. Now let's look at something very much simpler. And that's the idea of extending the field of the ultrasound image by moving the probe. This is described generically as being extended field of view imaging. Some of the companies refer to it as panoramic imaging. It's very much like the technique used with digital cameras to produce panoramic views by stitching images together to produce a wider total image. So the idea is if you are scanning a particular region, you activate this particular mode of operation, and then you slide the probe carefully along the patient's skin surface, being careful to maintain the same scan plane consistently. You will then be acquiring a series of overlapping images. The machine analyzes these images to see exactly how they line up with one another, and it stitches them together to produce a larger extended image. Let's look at one example. Here we have a conventional image of a liver, and now here on the right I'm showing you an extended field of view image of the very same liver, and the user has simply slid the probe along the patient's skin surface and acquired a much more extended field showing virtually all of the liver. So this is just a useful little add-on which has been available in ultrasound machines for quite a long time. So let's review what we have looked at here. I've explained the concept of speckle tracking and how that is applied to strain imaging. Then I've talked about strain-based elastography, where you are really just displaying a strain-based estimate of the relative stiffness of tissues. And then shear wave elastography, which uses a different technique and acquires actually quantitative measures of the Young's modulus, which is a measure of tissue stiffness. Then I talked about the plane wave imaging that is necessary for shear wave elastography, but which may well become the future of ultrasound, providing high imaging rates, much higher imaging rates than at present, and images that are focused uniformly throughout. I then show the application of this to vector velocity imaging, and then I briefly describe the idea of extended field of view imaging. So this is the end of this series of lectures. I mentioned at the beginning that one of the hallmarks of ultrasound imaging and ultrasound technology is constant change, like so much of technology. And so you will no doubt see new techniques, new capabilities, new concepts being introduced as time passes. So I hope this has proved useful and interesting to you, and I wish you well.